Welcome to Ask and Learn.
In this problem, we are given information about the reaction for the production of ammonia gas from nitrogen and hydrogen gas. Since this is a gas phase reaction, we can define the equilibrium constant K to be a Kp value in terms of partial pressures of these gases. And this comes out to the partial pressure of NH3 gas, since it's a product, it goes on the numerator, raised to the power of 2 due to its stoichiometric coefficient, divided by the partial pressure of N2 gas raised to the first power, multiplied by the other reactant, the partial pressure of hydrogen gas raised to the third power. In part A, we want to find the temperature when this value, Kp, is equal to 1. Remember that when K equals 1, it means that the reaction is at equilibrium. And when a reaction is at equilibrium, it also means that the change in Gibbs free energy is equal to 0. We are told that delta H and delta S do not vary with temperature, and so therefore we can conclude that these are constant values regardless of what the temperature is. So if we can calculate delta H and delta S, and we know that at equilibrium, which is what we want, the condition that we are given in part A, we know that delta G is equal to 0. We can solve for T using this equation. So that's the method that we are going to use for part A. We first need to find delta H and delta S of reaction using these two equations. For delta H, we find the total change in enthalpy of the products and subtract the total change in enthalpy of the reactants. For delta S of reaction, we find the total entropy of the products and subtract the total entropy of the reactants. Starting with delta H of reaction, we can find the total enthalpy of the products and the reactants. Starting with the products, we see that 2 moles of NH3 is the only product being formed. So that's 2 moles of NH3 multiplied by its delta H of formation value at standard conditions, which we can look up in the appendix. And when we multiply those two values together to cancel units of moles and yield kilojoules as a total energy unit, we get that value. For the reactants, we have N2 and H2 gas, which both form naturally, and therefore their delta H of formation values at standard conditions are both equal to 0. And when that's the case, it means that the total change in enthalpy of the reactants for this reaction is equal to 0. And so that means that delta H is enthalpy of the products minus the reactants, but the enthalpy of the reactants is 0. So delta H is just equal to the enthalpy change of the products, which is what we calculated previously. And now for delta S, we again start with the products. We see we have 2 moles of NH3. This time in the appendix, we look up the standard molar entropy value of NH3. And after we cancel out units of moles, we're left with entropy units of joules per Kelvin for the total entropy of the products. And now we see 1 mole of NH2, 1 mole of N2 that is, and 3 moles of H2 are the reactants. 1 mole of N2 and 3 moles of H2. In the appendix, we can look up the standard molar entropy values for each one of those chemical species, multiply them together, and then add them to get the total entropy of the reactants. Then we take the total entropy of the products and subtract the total entropy of the reactants to get the overall change in entropy for this reaction. And now we go back to this equation, delta G equals delta H minus T delta S, and we can rearrange it to solve for T. And this is the expression that we get when we do that. But remember that the equilibrium condition of Kp equal to 1 means that delta G is equal to 0. So we can get rid of delta G since it's equal to 0. And we're left with negative delta H divided by negative delta S, and we can cancel out the negatives to leave T equals delta H divided by delta S. We just solve for delta H and delta S of this reaction, and we need to just convert the units so that units cancel out so that we're left with units of Kelvin for the temperature. And so we can do negative 91.8 kilojoules was the delta H, but we can multiply that by 1,000 to get it in units of joules, so that we can cancel off the delta S that we just found, which is in units of joules per Kelvin. That was negative 197.3 joules per Kelvin. And again, the reason we converted the numerator into joules is so we could cancel off that unit and find temperature at which this reaction achieves equilibrium to be 465 Kelvin. And that's the answer for part A. In part B, we want to determine the value of Kp when this reaction takes place at a temperature of 400 degrees Celsius. This is the equation that we use to find K at a given temperature, but we need to first find the delta G at this temperature using that same equation, delta G equals delta H minus T delta S. Since again, we were told in the problem that delta H and delta S are constant and therefore do not change with temperature. So delta G equals delta H, which is again negative 91.8, and we'll convert it into joules again by multiplying by 1,000 for the purpose of canceling out the units appropriately. Joules per mole minus that temperature converted into Kelvin is 673 times the delta S, which was negative 197.3 joules per Kelvin. That comes out to a delta G value of about 4.1 times 10 to the power of 4 joules per mole. And now we plug in that delta G value at that given temperature into this equation to solve for Kp at that temperature. So Kp equals e to the power of negative delta G, which is what we just solved for, 4.1 times 10 to the 4th joules per mole, divided by RT, where R is 8.314 joules per mole times Kelvin, times the temperature, which is 673 Kelvin. We see that we cancel off units of Kelvin and joules per mole in the numerator and denominator so that we can take e to the power of this dimensionless quantity. We get a final answer of Kp at 400 degrees Celsius of 6.59 times 10 to the negative 4th. And in part C, we are told that when this process is run in industry, it is usually done at higher temperatures. And we want to explain why that is a reason. If we go back to what we did in part A, we know that we calculated the temperature at which this reaction is at equilibrium, and we saw that that was 465 Kelvin. At that temperature, Kp is equal to 1, meaning again that it is at equilibrium. We compare that to what we did in part B. We see that when we used a temperature of 673 Kelvin, which is greater than the temperature of 465 Kelvin that is required for this reaction to be at equilibrium, that the value of Kp decreased to be less than 1. And when K is less than 1, it means that the reactants are favored. So when we run this process at high temperatures, or at least temperatures above 465 Kelvin when this process is at equilibrium, because this reaction is reversible, the reactants of N2 and H2 will be favored to establish equilibrium. And because of that, our yield of our desired product, NH3, will be hindered. And so we want to explain why this process is still run at high temperatures, even though the value of K decreased, meaning that less product is being formed. And the explanation for this comes from concepts related to chemical kinetics. Remember that as temperature increases, the reaction rate increases. So thermodynamically, we are getting less NH3 being produced from the process at higher temperatures. However, the rate, which is all about the timing of this process, is higher. And when we have a higher rate, it means that we can produce more product in a shorter amount of time. And so in industry, it's more important to be producing product in a short amount of time than it is to be producing a lot of product but in a longer amount of time. And so that is why in practical applications, this process is run at higher temperatures.